again here at a simple example with a single converter to grid. And this example here, it's also just meant to illustrate stability problems and to show what kind of information we get out of modal analysis. And in this case, it has been kind of poorly tuned here. It's well tuned, but it does not consider here that you would have a capacitive load. So it would work very well without this capacitive load. But for the actual network where we are testing it, it has a tuning that it's not good. And if we look again, we see something very similar here to what we saw in the previous example, that we have something here that we are at an unstable equilibrium, but so as soon as we perturb the system, you excite here a harmonic instability, and we end up with having very large harmonic distortion. And this is a 60 Hertz model, so we have the fundamental here at 60 Hertz, looking at the Fourier transform of the phase voltage. We see we have an additional peak here at 60 Hertz plus 70 Hertz, or I think rather 79 Hertz. And two curves here also to illustrate what is the difference between simulating here with a switched model and a continuous model. We can definitely see that we have a little bit different results, but qualitatively the results match very well, particularly in the Fourier transform signals. And here we can look again here about this system matrix. So we use the same procedure here. We take our complete model, we make a continuous approximation of that model. Every simulation tool would internally calculate this Jacobian, so we can export that Jacobian from the simulation tool, and we get our A matrix. And here it's interesting to look at the structure of that matrix. So it will be a sparse matrix here. So this is a small system, so you can't really see that it's very sparse, but when we start looking at large scale systems, so when you analyze a wind farm, for example, you may have 100 wind turbines, or the newest project I'm working on is the Dogger Bank project, where we have 128 wind turbines. And then you end up here with a dimension of this A matrix of maybe 5,000 or 10,000 by 10,000. So it's quite large matrices. And on each axis here, both this axis and that axis, we have the dynamic states in the model. So for example, DQ voltages in the capacitors and inductors, we have dynamic states in the integrators in the control system, and we have various states related to delay approximation. So that gives us some physical insight about what is going on in the model. And so the first way now to explain how this modal decomposition works, we get here through the linearization an equivalent linear, approximate linear representation where we have a state derivative is equal to our system matrix times the state itself. So we can use this differential equation here to predict the evolution given a certain initial point or an equilibrium point, and giving a small disturbance around that using this matrix exponential. So if you solve this differential equation analytically, we end up with this matrix exponential here. And going back to these linear systems mathematics courses that most of us took, we can remember here that you can calculate this matrix exponential using the eigenvalues and the eigenvectors of the matrix A. And so it's basically a sequence of terms here, one term for each eigenvalue, and you could essentially predict the system's eigenbehavior using these equations. So we can rewrite this time response here, given the initial state, using the equation at the bottom. And finally, we can expand it here into terms on different forms, where you have an exponential part here, where the eigenvalues appear as the exponent here. Alpha I is the real part of the eigenvalue, and we have sinusoidal cosine and sine terms here with a frequency that is identical to the imaginary part of the eigenvalues. And this is a very useful representation to assess stability, because based on this form here, we can clearly, just by inspection, see here that the eigenvalues can be used to characterize the stability of the system. So if you end up here with an exponent alpha I that is positive, it means that this part here is exponentially growing, and you have something that is going unstable. You can here, if you have a complex eigenvalue where the omega is non-zero, we will see that it will have also will be an oscillatory instability, and the frequency, so these are the resonance frequencies that are given by the imaginary part of the eigenvalues. And we usually define here three different things. Here we define the attenuation, which is basically a measure of how quickly any instability will grow or any perturbation will disappear from the system in case the alpha is negative. We could talk about the resonant frequency or the mode frequency, which is given by the complex part here, and a damping ratio that can be defined based on those two previous things. And
but is it not damping ratio should be the negative, or are you taking this? Is alpha I the real part of the eigenvalue?
Alpha is the real part of, in my definitions, alpha is the real part of the eigenvalue.
But in that case, the
if alpha is negative, this term is decaying.
So in that case, the damping ratio, positive damping ratio.
So is there a missing minus sign here?
Yeah, there has to be a minus.
That's possible. I trust you on that, and change the slide.
Because then you always take the positive damping ratio as the stability.
Yeah. Yes. And if we, as an illustration of this modal decomposition, it's just useful to look at, say, how do these individual terms or individual resonance mode form our total response. So we have, in this simulation here, there was an instability in the PLL angle. And what you will see here in the top half of the figure, we see the contribution of a certain mode or a certain eigenvalue. And here we see how the dashed curve here, the total, this is the total system response. So we see there was a slowly growing instability here at a certain frequency, and the blue line will be the contribution of each mode. So if we look here, what you get from the first mode, we get one blue sinusoidal that you can see here. And we go to the second mode. Here we have now added the second mode. We are almost now at the final response, at least after a few seconds. And we can continue and add more and more modes. And in the end, we come here at the end with we see we have very fast modes left. So these are just some filtering modes that are barely visible in the time response. So we have already here almost perfect approximation. And if we continue and add all the modes, we end up with the exact same response that we would have gotten if we did everything, if we just computed the response using our original A matrix. And this also shows here that this modal decomposition, it's a very good tool for model reduction. So you can rank the importance of these modes based on the eigenvalues, and you can choose to cut off here. So you can use this, it's one way of doing linear model reduction. I will try to. Once you have those definitions here of the damping ratio and the attenuation, the final thing to look at are the participation factors. And we talked before about this part here, given the real part of the eigenvalue that predicts stability or instability. We talked about the oscillatory part that predicts the resonance frequencies, and you see there is another gain factor here, which we call a participation factor, and that participation factor can be computed here using the eigenvectors, the right and left eigenvectors that you will usually get as a byproduct when you calculate the eigenvalues, and arranging that in a special pattern. You can calculate here another matrix with participation factors, and these participation factors has a very nice physical interpretation, because you can use that as a measure of how much each dynamic state participates in a resonance mode. For example, here, if we take again our example, there was an instability at around 70 Hertz. One of the resonance modes has a positive real part and a negative damping. And what we can do now is we can rank the dynamic states in the model given that participation factor matrix. We can see which of those participation factors have a large magnitude for each resonance mode. So the dominant, that's what we call the dominant state. So here we already know by looking at that participation factor that the instability that we see is connected to this state in the PLL integrator, and already that gives us quite a good clue to how we should retune the system, to stabilize it. It's also for some other modes here that in this case are well damped. We can see that they are. One can see which parts of the grid is participating in a resonance. And I typically use these types of bar charts here, where we rank the dynamic states for each resonance mode. And you can use that here to figure out that the instability that we saw was related to the PLL integrator, its interaction with the grid inductance, so that's L1, and the capacitive load, the C. And also some participation here from the current control, but it tells you what is the first place to look if you want to improve the stability. And second step here, I also use something I call modal sensitivity analysis, and what you do then is that there are actually two ways of getting at it, but the easiest way is just to do repeated linearization and repeated modal decomposition, where you have perturbed your tunable parameters a little bit. So you basically calculate the sensitivity between changes of certain parameter values and the damping to the left and frequency to the right of the resonance modes. So again, here in this example, we have considered here a number of controller parameters in the control system as tunable. For example, the PLL gain, the current control gain, that's the KPI, the integral gain of the current control, and some of the grid parameters. And here the magnitude of these shows you basically what kind of, how strongly will the resonance mode be affected by changes in that tuning parameters. And here the sign basically means here that if I were to increase this PLL gain further, I would get a further negative damping. So here we can conclude that decreasing the PLL gain will be a good idea to get a better damping. So my 79 Hertz, this is my unstable mode here. And so these types of plots here, it gives you a very good idea about how to change the tuning. And you can also, what's important to check is here the effect it would have on the other modes, because often when you stabilize one resonance mode, you will do something to the other resonance modes. Another general rule here is that when you select what parameters to change, you should focus on those parameters, or you should at least check that it doesn't have too much of an effect on the frequency. Because if you change the parameters such as the frequency changes as well, it means that you are not only providing better damping, but you are forcing the resonance frequency to change. So it's not a really effective way of improving the damping. So that's a good clue to that. Maybe you should look at other parameters, or maybe think about if you cannot find something that is as clear cut as this example, that you should think about adding additional compensation loops and things like this. So from this parameter sensitivity, we can just validate that it works. So if I selected here the PLL gain, so I reduced the PLL gain to half its value, we see we have a nice, stable, well-damped PLL response. We could see from this part here that this bar tells me that if I were to increase the capacitive load further, I would get worse damping. So if I decrease the load, I can at least stabilize the system. And the same thing with the grid inductance, that if you make the grid stronger, these sensitivities would also tell you that if I decrease my LG here, that's the grid inductance, I would get a better damping. And that's also confirmed here by the simulation. So going back now, we already touched this a little bit. So, but I want to make a special point here, because what you often hear is that you cannot use modal analysis because all your models, like the cable models and so on, are given in the frequency domain. And but as we discussed now, there are various ways of transforming these frequency domain models into state space models and then incorporate them in modal analysis. And just to show you an example of when you do this, we have here the option of either doing here impedance analysis based on analytical models derived, say, by component modeling, or we could use identified models. So in the identified model, what I have done is I have run simulations with perturbation experiments. From that, I estimate the impedance, and from the impedance I estimate a state space model, and ideally now we should get the same results regardless if I use exact models and identified models. And you can show here are the generalized Nyquist curves for this unstable case, and we can very closely match here the stability results with the exact models and identified models. Same thing, we can do this now also with modal analysis. So if you use black box models in modal analysis, here to the left, it was the results we were just looking at. We can classify here stability, identify the unstable resonance mode, and we can figure out that it's related to the PLL. If I use a black box model, I will not have that physical insight anymore. So what I get out here as a dynamic state, a dominant state, is just you get the general location, but you no longer know exactly what control loop it relates to and so on. So, but it's still, say, in a large system setting, it's still very useful to figure out, say, which grid components and which converter is interacting. So, so if we summarize this part here, we have here a very well proven and rigorous mathematical framework. It's been used for a long time, many applications. I think the use of modal analysis, it really actually started in mechanics and acoustics, but it has been used also in the power system domain for a long time. And if you go back to more than 100 years ago, a couple of 100 years ago, we have actually the mathematics defined by these guys. And the whole thing is based on using the eigenvalues and eigenvectors. We can do predict the stability, and we can identify root causes of stability problems. And not shown yet, but that will be in the example. We show how we use this for very large systems with a lot of converters. However, here there are a number of things one need to very carefully model things, use proper approximations for delay and switching behavior. But if done properly, it is accurate up to about half your switching frequency, which is usually lower than your sampling frequency. So often the switching frequency is what is limiting the accuracy. And yeah, of course, the modeling of grid components, it's also uncertain in the high frequency range. But given that we have good component models or trusted component models, we can reach this accuracy up to half the switching frequency. So that wraps up, say, the main theoretical part.
Great. Any questions on this part? Okay, there is no.
It's probably quite basic, so we can move on to something more difficult.
Yeah, well, it's okay. When all our these attendees are our ESRs and master level students, so that's fine. But this was necessary for the future.
Yeah.
Next year.
So now for something maybe more novel and not so straightforward, and this is basically describing some work we had to do here to get our large HVDC and FACTS systems into the stability analysis framework. And For that, it's useful to look at here what is the physical layout of a typical HVDC converter. So a modern HVDC converter is of multi-level type, and it means that it has a structure here that you see to the left. That we have a PCC or grid connection here, and we have some phase arm inductances, and then a stack of individual switching modules. So in a modern HVDC system, we stack about 200 of those cells. And that allows us then to create a very smooth output voltage with low harmonics. It reduces here significantly the need for filters. So most often there is actually no harmonic filter in a MMC converter if you don't consider these arm inductances as a harmonic filter. And the first step in modeling this is that you can create here as what we call a single arm equivalent of these stacks here. Basically, this is a representation of each phase in the MMC converter. You can model it here with a controlled voltage source and a capacitor that is charging or discharging, depending on how many cells here are inserted in each stack. And the number of cells you insert here will, of course, then determine what is the output voltage in that phase. And so we can set up here a model which will be formulated in terms of the upper and lower arm currents here. This current through that valve stack and that current here, the lower arm. And those will be governed here by some inductance, resistive inductive behavior here of the arm inductance. But in the end, when you have three of these in parallel, one for each phase, they will together form here the DC voltage on the side. And we have some other internal dynamics we have is due to the charging and discharging of the capacitance. And we can already see here that this is a little bit more complicated than what we considered so far with the two-level converter. Because you have here the VCU, that is the capacitor voltage here. This is a dynamic state in the model. So we have a derivative here before it. And the NU, this is the insertion index, which is basically the percentage of cells that is inserted. And we take this dynamic state and we multiply it with an input, so we have a nonlinear model. And nonlinear models have this nasty property that if you drive them, if you have already some variations of, let's say, resonance modes or variations in the states here, and you multiply them, you get new frequencies. So this LTI model, it's basically based on the assumption that we have only 50 Hertz variations. But now we will multiply that. We multiply our 50 Hertz variation in something here. We multiply it with a reference that also has the 50 Hertz. You end up getting 100 Hertz. And then that 100 Hertz gets multiplied again. And in principle, you get an infinite number of frequency components of the variations in the model. And that basically breaks this LTI framework that we discussed now. So we came up with this, I don't know if someone else has done it before, but we call it this generalized EQ transform. And what you do then is that we use the classic, same idea as the classical Park transform, where you would only have the first columns here of this transformation matrix. So apart from the scaling here, this is, if you cut this off here, it would be the same as the normal Park transform, but we consider here additional terms here with higher frequencies. So we no longer get only one DQ frame, but as many DQ frames as we need to represent the behavior. And you can do this, the model transformations that we were talking about for the DQ, the normal DQ case, you can use them also for the generalized DQ case. So we can use here, you end up with a lot of chain rules, and you can do coordinate changes to recalculate derivatives that you had in the ABC frame and represent those in the DQ frame.
So could you, sorry, I'm interested in particular this. Could you quickly explain how the TN matrix is made up? Because I'm a bit confused in the second line, the second term, you have an N, it's 4NP/3. I guess that N is probably like a typo, right? And then it's just increasing with N is the harmonics that you want to represent.
Yeah, so this transformation matrix T here, what you would start here is, these are the group for the normal DQ frame. And then you introduce here for N equals 2, you get a second DQ frame for 100 Hertz. And for equal 3, you get another DQ frame for the third harmonic for 150 Hertz. And then you can increase this higher and higher. And the main difference here between the original Park transform and our generalized DQ transform is that in the Park transform case, this is a bidirectional transform. You can go either way. But in our case here, we can only go one way. We can always go from the DQ back to the ABC, but not the other way around, because it's not, you don't have enough information. So so here, if we have any signal here in the ABC frame, we represent that here with the DQ components of the same. So you see you have here, depending on the order, for order 3 here, you would have 7 components. So the 0 component, the first harmonic, second harmonic, and 2 for the third harmonic. So can you repeat the question again? I don't think I answered it right.
I think it became clear. Like, I think it's just a typo in the TN matrix that you show. Like the element 2 has a theta minus 4n pi/3. But I assume that like this n should be. Like,
oh yeah, there should be n's here. There is a missing n here. Yeah.
Okay.
Or no? Yeah, I think so. Yeah, this is very likely that there could be some problems here. I can check that. But I think the principle is clear. And,
yeah, thank you.
And that means now that we had this model in the stationary frame where so we can quite easily derive this. So if I want to transform this now into the generalized DQ frame, what I need to do is I need to take all these derivative expressions. I need to substitute those here with one derivative of the DQ frame in the DQ frame, plus here a term k times the state itself. And this k matrix here is basically derived from the chain rule that we need to apply. So you can set up here a k matrix where you have 0, 0 for in the top left corner, and here you would have synchronous frequency until you get to n times synchronous frequency here. And so that's kind of the first straightforward part of the transformation, and this is actually not an approximation, it's still an exact representation. But my problem here is that when I tried to look at these terms, they appear here, the where I multiply my insertion indices with my state. It appears here, here, and also for the capacitor voltages. I have something here with a certain number of frequency components. This one also has the same frequency components, and you end up with something that had twice the number of frequency components that you started with. So what you have to do there is to take this multiplication, represent it in the generalized DQ frame, and there you have to cut off terms. And depending now on the choice of how many DQ frames you are using, this approximation error will get smaller and smaller once you increase n to a certain value. And we can look here at here again. This is an example for an HVDC converter. On the top here we see the capacitor voltages during steady state. The blue line is simulation with the ABC frame model, so what we consider the truth or our exact model, and the red lines are the DQ frame model. So here, even with the order of 3, you can almost perfectly represent your capacitor voltages. You can also represent here the PCC voltage. So if you're only interested in the, say, the AC side stability and interaction with other converters, you can typically get away with using a low order. However, here, once you start looking at the DC side, we see we cannot reproduce. There is one frequency component here that we don't see at all. So if we want to see those two, we can increase this approximation order, and you get successively a good match in more and more of the quantities until the highest order we tried was 17. And you can more or less get to an error that is you cannot even see. And so the tricky thing here is that in order to find those functions f here, you need to do a lot of symbolic manipulation. So I did it with the symbolic toolbox, and once you reach 17, my computer ran out of memory. But in principle, you could go to any order. In practice, you don't need to go, say, beyond 7 or so, I would say. And this gives us here, whereas this original ABC model is completely useless for modal analysis, with this generalized DQ model, we can embed it in stability analysis. So, but you would get some interesting effects here, that because the dimensionality of the model, it increases with the number of DQ frames I'm using. We get more resonance modes in the higher order model, and but what you can see that in the high order model we have the same attenuation. So the decay of oscillations or the amplification of instabilities will be predicted to the same value, regardless if you have a low or high order model, but you will not see the details in the simulation results. So this part here, we present here this generalized DQ frame model. There are many papers written on MMC model for stability studies, but this is the approach that we chose in the end. We achieved this main objective of getting something that is compatible with the modal analysis. Usually you can use an approximation order of 3 to because usually we study mainly the AC connections. The DC side is quite well known in at least a point-to-point HVDC link. So we are usually interested in the AC side, and the reason we use 3 here is that we also have a third harmonic injection. So otherwise we could get away with using approximation order 2. And yeah, so when you start getting many of these models in the same simulations, of course the deciding factor that eventually things are getting too complex if you increase the approximation order too much. Any comments or questions on this section? Additionally,
question, someone raised the hand. Okay, let's see.
Okay. Good afternoon, Dr. Larsson. My name is Zhu. I'm from the University of Warwick. And my question is that when you try to linearize the system, I mean the wind farm or the HVDC, because it will be very complicated as the system is very large.
Yeah.
So do you have some valuable experience to share with us about your linearization work?
Yeah, so I mean, the first point here is that I never derive these expressions for the A matrix by hand. So I'm using a special tool called Dymola. So that's a simulation tool, but it is, you could say it's similar to Simulink,
Okay.
but it has a little bit better support, particularly when it comes to modeling grid components.
Okay.
But that allows you then to use automatic differentiation to get these Jacobian elements. And this is also very important because often when you start increasing the model size or the model order, things also get, say, poor numerical conditioning. So if you use, for example, finite differencing to calculate Jacobians, you end up having problems because they are not accurate enough.
Yeah.
So the choice of tools is quite important.
So you mean the tools that you have used can also linearize a very big system, such as many wind turbines that connect to a point-to-point HVDC or multi-terminal HVDC systems.
Yeah, I mean, we have used it for almost everything. That we used it for DC grids. We have used it for large wind farms with 100 wind turbines. We use it for grid systems with frequency-dependent cable models. But there is, of course, special modeling considerations for each of these things. But scalability is basically not a problem. So I mean, with today's computer, looking at this largest wind farm, it takes about 20 seconds to compile and linearize the model. So to analyze one operating point. And about half of that is to calculate the Jacobian, and then you need to calculate the eigenvalues of maybe 10,000 by 10,000 matrix or 20,000 by 20,000.
Yeah.
And what we didn't explore yet, we have this second step there of calculating eigenvalues. There are special techniques to calculate eigenvalues on sparse matrices that could speed that up, but so far, I have not seen the need to do that, and it's also I tried it, but you get some problems with the convergence and numerical stability and things like this. So I do not use this sparse mathematics for eigenvalues yet.
Yeah. Also, when the system is large, then a state will be decided by many factors, and so you will get the participation matrix, but just oscillation model may be dependent on many states. So when you face that problem, how do you regulate the parameters in order to dampen the oscillation to improve the eigenvalues?
Yeah. So, but this system matrix you get, it actually contains all the information about the couplings between the different wind turbines, for example, in a wind farm. But maybe one thing that is a problem, it is that say that you have in a wind farm you would have say 100 copies of the same control loop.
Sorry, the signal is bad.
Okay. Is it on my side or the other side? Because is it okay for you?
It's your side as well. I can hear clearly.
Yeah, I can hear Max clearly, and also Zia clearly. Okay.
But one interesting problem that comes up is if you have then a very large wind farm with say 100 copies of the same thing. For example, the current controller in a wind turbine, and it means that when you calculate participation factors for the state of that, it will be a very small value because it's only 1 out of 100, and that means that. You may need to look for, say, ways of grouping the states based on their names and so on to really figure out the importance. But usually what I do is I look at the damping, and I first or damping or attenuation, and that is basically my ranking criterion. And then you have to look in detail, maybe plot the participation factors of hundreds of states before you find real root causes.
Yeah.
And but there is also my life is a little bit easier there because I'm at Hitachi ABB. We actually do not make wind turbine converters anymore. This is one of the parts that went out to the ABB in the split. So I'm focusing mainly on the HVDC side, and there we have just one copy for each wind turbine, the wind farm at the moment. But it is a valid concern, and it can make things a little bit tricky to interpret.
Yeah.
Okay, thank you, Johan.
Okay, thank you.
Another question is from Nicolas Cifuentes. Nicolas, can you ask your question, please?
Yeah, thank you, Professor. I was just wondering if you have tried to apply the impedance measurement and system identification techniques to the MMC converters, as you explained in the previous presentation.
Personally, I have not done it, so I don't have any detailed knowledge, but I know we have done it in-house by other people. So we have developed a detailed representation of our own HVDC converters in this modeling framework I'm describing. So we have an analytical model, and we also have, say, a very detailed PSCAD model that includes the actual control code and as close as possible every delay we have in the system. And based on that model, we can run, say, simulations with perturbations in PSCAD, and from that calculate impedance matrices. And those impedance matrices have been compared with our analytical models. And we have found the agreement good, but I have not been personally doing this, say, these numerical calculation of impedance responses. So if you have detailed questions, I'm not sure I can answer, but you can try.
I think, Matt, that's a very honest answer. Now, the point could be that because you are Hitachi ABB, you have all the detailed model, and you build your own converters, and you have your own, say, TSCAD model. Now, when it comes actually that wind farm is getting connected to the grid, or say a big an HVDC system is connecting to the grid with all this MMC based technology, naturally the network owner or even network operator would like to see that rigorous grid connection studies are done, the stability evaluation, etc. Now, if that is being done by somebody else who do not have access to this sort of detailed model, naturally then they have to resort to some kind of black box model where you have some input and then you get some response, and on the response you apply your tool to find out or construct an impedance model. So I think that is the perspective that Nicholas was coming from. Is that right, Nicholas?
Yes, exactly. So I was thinking from the black box perspective, if it's possible to come up with an LTI model of a MMC converter based on measurements using system identification techniques, such as the ones you proposed by the end, I think, of last presentation. So you mentioned that you applied vector fitting to the impedance behavior of a converter, and you had very good matches with the simulation. So I was thinking if you did the same for the MMC converter.
Yeah. So what we are doing with this MMC converter there, so internally we have a representation with the multiple DQ frames. We need that to model what's going on the DC side, and we need it to model what is going on in the control system of the HVDC. But you don't actually need it to model what comes out of the converter on the AC side. And the main reason for that is that you have always a Y delta transformer, and that blocks your third harmonic. It blocks your zero sequence. And what you have left then is your fifth, seventh, and what's coming over there. You could in principle go to infinity. But we are using then, you have a lot of clever tricks in the control to make sure those are not visible in the AC quantities. So in my experience, the single DQ frame model for the grid is very good, even for an MMC converter.
Yeah, but we are more interested for the the multiple DQ frame for the MMC converter that is sold by generalized transformation.
Yeah. So the multiple DQ frame model is more relevant, say, for cell balancing controls and control of the DC side than for the AC side control.
But it also depends on Matt. When you talk about the grid as DQ single, it also depends how your grid. I mean, is it perfectly balanced?
Yeah.
Feeders are all symmetrical, transposition. I mean, there is always some, element of assumptions.
Yeah. Actually, I should have mentioned that when we had the previous section there. When you use the DQ transform, we always assume we have a symmetrical system in the stationary frame. Okay. And that can sometimes give rise to problems. For example, I got some cable data from the Danish TSO. So they have a lot of cables on the high voltage network. And when you have them on the high voltage network, often you have this flat formation cable. You don't have all three phases in the same in the same cable. You have one cable per phase, and you do not lay them in a symmetrical formation. And that means that the impedance matrices you get are unsymmetrical. And that has some effects at higher frequencies that you need to approximate with these modal analysis methods.
I mean, and then single part transformers will not perfectly decouple that also. That's the problem.
Yeah, but I did not see that I got any particular limitation with relation to the MMC dynamics for that. It's more about the grid and whether the grid is symmetric or not.
Okay.
Because in the converter we have then controls that tries to keep it symmetrical at all times.
Good. Thank you. Any other questions? If you don't have, then we could move to the next section.
Yeah. So I will probably warn you that we may need we need a little bit more time, so we can choose when we finish the first case study whether we want to have the second one too, or but I think from the questions I gather you are interested about scalability and what we have done to apply this in practice. So that's about this section. So we will look first at an offshore wind farm, which is inspired by this wind farm. So I'm not really allowed to show you the models and detail the network, but some of the measurements are of course from the real system, but with the most of the analysis results are based on a generic wind farm model, but very close and inspired by the actual farm design here in the Bard farm. And hopefully you remember this about the harmonic problems and the interharmonic instability. And we discussed there that this type of problems are connected to harmonic resonance, and those say we are now moving more from a static viewpoint into a dynamic viewpoint where we can include also the effect of control. But in principle, this type of figure still holds here. We can use the impedance response to predict resonance points. And when you run modal analysis, you would see now that these resonances are visible also in the modal analysis results. And you will calculate damping, and those dampings will be related here to the sharpness of those peaks and valleys. And so the root cause of this, I would classify it as an interoperability issue that due to resonance between the complete system, including the wind turbines, the cable system, and the HVDC. And one should note here that this was back in, now we know a lot more than what we did at that time. And actually no one really experienced this type of problems on this scale before, and there was no studies really study requirements from the customer or by regulations, and but given the learnings from what we learned here, so the whole industry has learned a lot. So as we said before, there are still a lot of ongoing working groups trying to make sense of this, but I think we have gotten to the point now where we can be quite confident. And here, a simple way of understanding these problems is if we calculate here the incremental impedance seen at the PCC of the HVDC in the system as it was running. We had here a number of resonances related to, these resonance peaks here, they will shift around depending on how the cable network is configured, how many wind turbines you have online, and even you will have a small variations here depending on the operating point. But the problem here is that there was harmonic injection here presumably from the wind turbines, because we know that DFIGs can generate this type of slip harmonics around this frequency. And And that caused these problems because it's very close to this resonance. And we designed then, we have a switching frequency of about 1.6 kilohertz in that HVDC system. And 290 hertz is well within the Nyquist frequency. So Nyquist frequency will be around 825 hertz. So we were able here to design some damping that could reshape the impedance curve, so that instead of having the original red impedance curves, we could shave off the peaks of these resonances, so that the same harmonic injection we had that was catastrophic without the damper is more or less completely harmless when the damper is activated. To get to this conclusion, then we needed to drill down on this using modal analysis, calculating resonance modes, looking at controllability from different points, and so on. So you can see on this plot, we see an actual field measurement from the BARD system, from the Borwin and BARD. So the HVDC is called Borwin and the wind farm is called BARD. And here is a phase voltage measured at the HVDC. Should normally look like this with a little bit of switching harmonics on it, but in principle pretty smooth. One can see here from one event that it starts here. We can start detecting that there is additional harmonic that starts to grow. So you can see that as this jaggedness in the curves, and even at the top here we can identify again this 290 hertz frequency. But based on this, so we always analyze here the frequency content of the voltage, and we can trigger here a damping loop so that we activate the damper, and once we activate the damper, we create then when we had a negative damping, we create a positive damping until this is damped out again, and then it goes back. Slowly we have the damper activated. You see the distortion gets smaller and smaller, and eventually we are back to something where we can deactivate the damper again. And the concept we used here is known from literature before. It's a virtual resistor, and this you can see here in per unit the amount of voltage we need. So this is the voltage over a virtual resistor, and that resistor it corresponds to about 30 ohms. And you can imagine there, so we could actually have gotten the same damping with a physical resistor. And so the problem then is that you would have then losses that we have about 1.5 or 2 kiloamps rated current. So you would get several megawatts of losses in that resistor. So when you do this with active damping, that energy, it will be taken out of the resonance on the collector grid side, but it will be fed onto the DC link. And then it comes out the German end of the HVDC link as power that they can sell. And so to explain here a little bit, or we can provide some information about what can go wrong here. So we are now moving to generic models. So we're using not the type 3 wind turbines, but type 4 wind turbine models with the generic control systems. And but the control system layout is typical. The size of the turbine is aligned with the BARD wind farm. It's this previous generation wind farm with 5 megawatt turbine, 33 kilovolt collector grid. For the stability analysis, we only model the grid side control. We have a very simple model of the DC link here with just a current injector. and a DC capacitor. And control scheme is also simplified but typical, where we have current control in DQ frame. We have a DC link voltage controller and a reactive power controller that tries to control the reactive power to 0 at the wind turbine PCC. And so the first step here in the analysis, we can look at, gain some insights here from analyzing one of these wind turbines when connected to a strong grid. And from the modal analysis, we can see we have 2 resonance modes here, or even 4 in DQ, but 2 main resonances. One is what do we call an inner resonance? So this is basically related to the LCL filter in the wind turbine. And you have a lower frequency resonance here that depends on the LCL filter, but also depends a lot on the grid you connect to. So whereas this first one here remains, it doesn't change very much depending on the grid. This grid resonance here can change a lot depending on the grid. We can also identify that there are a number of resonances or a number of modes here related to the various control loops. So for example, the DC voltage regulator, current control, and but in principle, yeah, when you look at these dampings, they look perfectly acceptable. This is quite a nicely tuned wind turbine, and it works very well when connected to this grid. So now the next step will be to, now we come back to this, what can we handle with these tools? And if we look at, this is the layout of the barred wind turbine. So in that case, we had 80 wind turbines on strings with different lengths and a different number of wind turbines on different strings. But in total, there is about 120 kilometers of 33 kilovolt collector grid cable here. So if you sum up the length of all the short cable segments, and in addition here, there was there was an AC platform for the barred wind farm, and then the HVDC was built on another platform about 2 kilometers away. So there are also some high voltage 155 kilovolt cables. They are those cables you see here. And so when we take this model here and instead of, we connect here this wind farm with its collector grid and each of the wind turbines, and we do the modal analysis of that. So you can see the results to the left here, frequency of and damping of the resonance modes. Clearly, we can see here a group of resonance modes related to this LCL filter resonance in the wind turbine. We see the grid resonance here, and we see some other modes that are related to other parts, like the transformers and the AC grid cable sections. But these 2 groups here are clearly identifiable. And we will now make an experiment that what you see on the picture here, we have a very low production. So we will, if I slide here, I will increase the production. And I go up here to full power. And we see here that particularly the grid resonances that are here, they move, so they get worse damped. But in this configuration where I have a strong grid connection, this doesn't become critical. We still end up here with a damping of 15%, which is quite fine. So you would not notice that you have any particularly harmonic problems around this. It would damp out very nicely. So if we make a next experiment here, so we add transmission cable. So if this is an offshore wind farm, and we connect this to a AC grid onshore via a long AC cable, and we can make the same experiment. And so if I start here in the base case here with very low production, so 10% production, it still looks nice and stable. But if I increase the production, we see the grid resonance gets worse and worse. Firstly, they start from a lower base damping, but also eventually we can predict here an instability at around 90% production. And this can be also validated if we simulate this power ramp up. We start here from 10% production, we increase the production, and eventually we would see something similar to what we observed in this the real wind farm, that we ended up with a very large harmonic distortion around a frequency here that depends on the grid and the wind turbines themselves. And now we can go back here. We can look at the modal sensitivities, try to figure out, say, where are the root causes of this behavior, and how do we fix it. And again here we have the modal sensitivity plot. On this axis we have the resonance mode, so the main problems with the instability are related to this 196 and 104 Hertz. And we can see that there are strong sensitivities here to some control parameters. So this control parameter here, that is the KFF. This is the voltage feed forward gain in the wind turbine. So it is in the base case selected to have 100% feed forward. So if you were to increase it further, it would contribute more. So we can conclude that maybe decreasing this gain would be useful to improve the stability. The other strong sensitivity we can detect here is the current control gain in the wind turbine. So see the same thing if we decrease if we increase the current control gain, we would further worsen the instability. So that decreasing the gain may be a good idea to stabilize this. So as a verification here, we can reduce the feed forward gain. So instead of using 100% voltage feed forward, I simulate going down to 55%. And so in the beginning here, so now when I sweep here, I change the voltage feed forward gain. So we start with 100%. We have here an unstable mode, and we can stabilize this mode. So I have, based on the sensitivity, I calculated how much I need to change the feed forward gain to get a damping of about 15%. And now one can see from the other, it's important not only to look at the mode that you are considering in your tuning, but also the effect on the other modes. So we see that this LCL filter resonance modes get worse damped. So there is some kind of, with only this as a solution, one needs to somehow consider, we cannot go beyond this 15% damping, more or less. So in the next step, we will consider here a HVDC connected wind farm, and this is also loosely based on the HVDC system we were actually using in BorWin. So this is an older HVDC with a 2-level converter, 1.65 kilohertz switching frequency. We have a standard filter design, and here offshore we are using a grid forming control, and this one controls here the AC voltage and phase angle. There is no PLL. And we have basically controlling the AC voltage magnitude via a PI controller and a fixed phase angle. And the actual layout now of this older HVDC system is similar to the wind turbine with an LCL filter, but one of the inductors is replaced with a converter transformer. And we will basically see similar behavior as we saw with the cable connection, that in the base case we get an unstable mode here, and we would have an instability. We can run now modal sensitivity, but what we will change now, it will include also the control parameters in the HVDC, and in HVDC we have also a virtual resistor. Oh, not yet. We have included the gain of the AC voltage control, and but looking at the sensitivity, we figure out that the solution to this problem is more or less the same as with the AC cable. That it's strongly related here to the gain of the current control, to the voltage feed forward gain in the wind turbine. So we could fix this problem again by changing the current control gain of the wind turbine. And then you would see that if we decrease the current control gain, we end up again, we can reach a damping of about 15%. However, decreasing the current control gain, it's not necessarily something we want to do, because it may get much more tricky to fulfill fault right through criteria for the wind turbines. And so with the HVDC, we get another possibility here. So we can consider this a damping control loop in the HVDC. So it's based on lead lags. Those have been carefully designed here to consider the resonance frequencies. So what you do is you use the eigenvectors and you calculate modal controllability and observability, and you can use that to define here a compensator for the HVDC control. And starting here from zero gain of that compensator, we end up here, we start with the original unstable operating conditions, and we have designed here a gain where we would reach our target 50% damping. And this is much better than just to decrease the current control gain of the wind turbines for two reasons. So one is that you can maintain then the performance you expect from the wind turbines, but it also comparing the modal analysis, we see that the other resonance modes barely move when we had the damping in the HVDC. So in conclusion here, we can we can see that these the stability problems that we are seeing, they are strongly connected to the resonances of mainly the collector grid, but also the filters of wind turbines of HVDC. We see that qualitatively there is not a big difference using a HVDC connection or an AC cable connection, but of course quantitatively it will be different, and you need to consider tuning in different ways. We see that there is a strong sensitivity to the operating point. So the stability properties were always better at low power than at full power. And this can be explained partly by the nonlinearity we introduce with the PLL in the wind turbine controls. So we need to make sure that we coordinate the control of the wind turbines with the operating range, but also the cable system and whatever you have on the AC side, be it an HVDC link or an AC cable connection. But you can use modal analysis techniques to give support for the tuning, so that in this case it gave adequate damping. On the other hand, if we look at this offshore HVDC control we are using, or we are still using, we have a very simple control scheme. There is no PLL. We don't have this problem of nonlinearity, so we very weakly interact with this grid resonances. And you can also use the HVDC quite effectively to damp these resonances.
Good, great.
So that was the wind farm example. So questions and discussions. I guess this would be quite relevant to the WinGrid project.
Yes, yes. Now open to questions and discussions. And we did this. Yeah, please.
Sorry, I'm just asking like a very general question. The presentations that you show us, can you share them, or is it stuff that should be that you have to keep private?
No, I can make PDFs of these presentations and share them.
That would be very nice to have a second look at it. Some of them.
Yeah.
Oh, is that Florian from ETH?
It's Florian. Yeah. Sorry.
Hi, how are you, Florian?
I'm good. How are you?
I'm good. Yeah. Yeah, we did this PhD examinations last year with Elborg. Okay. This is really, great sort of work and learning in terms of the multiple generalized Fock transformations and then HVDC damping on a practical case. I particularly know this Bird wind farm where we did some work for Alstom grid, the type of things not happening in their Darwin 3 with Tenet. So these are really, really great stuff. All I want now is this, all the participants, if you have any questions or doubts, you could ask Max and we can have a discussion. There is, again, from Behnam.
Yes, thank you, Behnam from DT Wind Energy. And thank you for the great presentations. And actually, I had a question regarding this generalized DQ transformation. And yes, maybe it would help to have the equations.
Yeah.
Yeah, thank you. So would it be like correct to interpret this to say that you are considering kind of each DQ transfer for each harmonic, or let's say from the characteristic harmonics of the HVDC or any system?
Yeah, so I think so that you can. The whole thing starts basically with that you want 50 hertz here on the grid side.
Yes.
And you create a voltage reference that you feed into the modulation index here that is also primarily 50 hertz. We may be using third harmonics and so on, but to say for simplicity, it's only 50 hertz. And this means that you do get what we want, the 50 hertz here, but you also get 100 hertz on the DC side, because you basically multiply something that has a 50 hertz component with something else that has a 50 hertz component.
Yes.
And so you get 100 hertz, and then you take that one, and then you multiply that again with 100 hertz, you get 150, and you keep on going. So, and what we try with this generalized DQ transform is not to look at that here in the ABC frame as say you would plot the time series, but rather instead of tracking the signals themselves, we try to track the amplitude and phase of each frequency component.
Yes.
So it's exactly the same idea as the Park transform. It's just that we generalize it to more frequency. So I think the answer to your question is yes.
Yeah, and then for just more clarification to myself is that, for example, when you transform this, then for each harmonic, you have the DC value for that specific frequency, and the rest are oscillations. And then do you take the DC values in the output in these transformations, or how?
Yeah, so I mean, obviously, so here for the DC voltage, we have mainly the DC value. So this is very important for the DC side, of course, but we also do get the other components much smaller for the, say we may have a little bit of remaining second harmonic on the DC side, for example.
No, sorry. My question was that, for example, SD1, so you're taking the second order harmonic, and then if you transform the ABC values, then there will be one DC, which is dedicated for second order harmonic, and the rest, even the fundamental, will be kind of oscillating parameters in that transformation component, right, in SD. So you are somehow you need to also eliminate these values, right, the oscillating values for each transformation.
Yeah, I mean, when you use this transform, you would get something that agrees perfectly with your ABC model. So the effects that you are talking about will, I mean, you will see the effect of that in your ABC quantities, and you will see the effect of those also in how the DQ components vary. But as I quickly mentioned, I passed over it quickly when doing the explanation here. There is an important difference here between the normal Park transform and the generalized one, because the normal Park transform is bidirectional. We have the same number of components in the ABC and the DQ. Here I have many more. And that means that you need to use some knowledge about your system when moving over from the generalized DQ equation set in the generalized DQ frame here back into the single DQ frame we use for the grid. And I think this is connected to your question.
Yeah, thank you.
You may need to derive the detailed answer based on my explanation yourself.
Yes, and also I was actually interested.
You have to make assumptions there.
Yes. Yeah.
And one assumption is that the third harmonic doesn't pass through. And this is because we have a Y delta transformer. Yeah. So and the other assumption is that the zero component doesn't pass through. The zero current, the zero component doesn't pass through. And that gives you enough assumptions to handle the case of approximation order 3. Then you still have enough enough equations to go both ways. But you have to add these additional assumptions. But once you start going, say, to a very high approximation order, so if you have 17 here, we will have a dimension of this state, this vector here, that is 17 times 2 plus 1. And we need to map that to only 3 signals. And what you need to do then is to assume that the content, the amplitude in these higher order terms is small, so you can neglect them.
Yes. Yeah.
And you see the effect of that approximation, and also some other approximations we have inside in this plot, that you see even with a very low order, you have a very good match in the AC quantities. But for the DC quantities, you need a little bit higher approximation order.
Yes.
Great. We will have those slides. Second question, if we have any more, if we have anyone. Ben, you are still raising the hand, I guess.
Yeah, sorry, because I had another also, just to elaborate on this.
Well, let me ask. Give the opportunity to others also to ask some questions.
Oh, yeah. Okay. Sorry.
Yeah, there is one. Is that Nicholas?
No, Prof. I don't have any further questions. So.
Okay, that's fine. I don't see any other hands. So now, Ben, get back to your second question then.
Yes, thank you. I was wondering then in the final questions that the value of n, can it be non-integer value in this transformation?
No, not really, because you need to create here a dimension of this T matrix based on the selection of n.
Yes.
So it is an integer number, but it can be anything between 2 and yeah, whatever you need. We tried up to 17.
Yes, thank you.
Right. If Matt, you also mentioned that it all depends on the loading level, these interactions and all operating points.
I mean, particularly the things that you detect that is related to PLLs, and the interaction of PLLs and current control is also strongly operating point dependent. Yeah.
And once also you mentioned in your talk that if you could slow down the PLL by reducing the gain, but then if there is very stringent fall ride through requirement, voltage response requirement, so then there is again this set of converters on a grid following mode will not be able to restore the voltage very quickly, right? So there is always a trade-off.
Yeah. I mean that was basically my point with this slide here. That when we look at the effect of the HVDC damping control loop, that you can actually stabilize that kind of unstable dynamics using the HVDC control system. So when you just add this additional damper in the HVDC, we do not need to retune the current control. So you can maintain the performance of the wind turbine control while still managing the system stability.
Great. So
it's kind of pointing to the advantage of having an HVDC connection over an AC connection.
Yeah, I mean,
which I of course have certain reasons for promoting.
Well, particularly when there was this 2019, this 9th August grid collapse in UK with the Hornsey.
Yeah. I mean, maybe you have more information about Hornsey that I have, but as I understand it, the problem they had there was that
the dynamic reactive power support control loop, honestly.
Yeah. So it was essentially this situation here, where you have you have a wind farm, you have a long AC cable, and then you have a grid. What I didn't show in my slide is that if you change here this grid strength of the AC grid, the stability of the wind turbine control is very sensitive to the short circuit ratio in this end. And when you, what they experienced there was a weakening of the transmission grid. And now I don't have the details about that, but I can guess that they came out here with outside the range they have considered in the tuning.
No, I think the problem was different. I can send you some report. It is because there are long AC high voltage cables. They had the STATCOM, in between, and that STATCOM control loop had some kind of wrongly tuned with the wind farm.
So it was.
So it was the control loop. It was the control loop within the wind farm.
Yeah.
That was the problem. But grid changed, of course, its strength. But that control loop, they had some setting issues. So maybe some in a digital control, rather than a -1, they put a +1. So that type of thing happened. Anyway, so.